Well, all right, here we go with chapter 11 here. The notes for, at least the intro notes for 11.1, the chi-square goodness of fit test. And we'll talk about the chi-square, the distribution, and how it applies for a test of multiple comparison, ultimately, of categorical data. So it'll sound kind of like the proportions procedures, but this will allow us to do multiple proportions at once. So the chi-square goodness of fit test, we're going to talk about calculating expected counts. We'll look at conditional distributions. This is going to be like our two-way tables, ultimately, from chapter 2. And then how much does each category contribute to the chi-square statistic? We'll get to the random independent conditions. And then the third one is for large sample size. Very specifically, it is not a normal check. We're very used to saying random, normal, and independent, but that's not what's happening here. This is a different distribution. It's the chi-square, so not a normal check, our large sample condition. Then we'll, probably by day 2 this week, talk about the test and the 4-step procedure, the hypotheses, all the way to the conclusion. And then if there's any follow-up analysis, if in the chi-square distribution, if we end up rejecting the null hypothesis, that means that something is going on, and we'll then follow up and find out which category was most influential in that conclusion. In this chapter, we'll talk about the chi-square goodness of fit test to determine whether a hypothesized distribution is valid. That's what the test does for us. Later, in 11.2, we'll talk about 2 other tests. The chi-square test for homogeneity of proportions, and then the chi-square test for independence. The chi-square test of the goodness of fit test, the one we're going to talk about today, is for one population. And there's also going to be one categorical variable. The other test that we'll talk about later, the chi-square test for homogeneity of proportions, is going to be for 2 plus populations and one categorical variable. Whereas the test for independence is going to be one population, and I'll say 2 plus categorical variables. We're only going to deal with 2, but theoretically it could be more categorical variables involved. So the test today is 1 and 1, and then we'll talk about the other 2 where you've got multiple populations in the test for homogeneity, or you have multiple categorical variables for the test of independence. The famous example, those of you that maybe have done the chi-square procedure, I think AP Bio does this test, is we're looking to see, does a sample follow a hypothesized distribution? So for example, if the Mars company that owns M&Ms says that in any bag or in their distribution of candies for M&Ms, you should have 13% browns and reds, 14% yellows, 16% greens, 20% oranges, and 24% blues. If a bag contains 60 M&Ms, would your bag follow that distribution? So here's an example where we expect these orange counts here. This is out of 60, so this many expected blues, this many oranges, and so on and so on and so on. Now, it turns out in the bag, we had way more yellows than we were expecting according to that distribution. And I guess along with that, way fewer blues and oranges. You could throw browns in there as well. And so surely it's not going to fit the distribution perfectly. Hopefully by now we're not expecting that to happen. The question is that distribution of what we observed different enough from what we expected? That's the question that the chi-square tries to tackle. So here's the sample data. The count we had was we had 9 blues, 8 oranges, 12 greens, 15 yellows, 10 reds, and 6 browns. We could, you might be thinking to yourself, I could do a 1 prop Z test and just look to see, is this proportion of blues, 15%, equal to or significantly different from the proportion that we expected, which was for the blues 24%. We could do that 1 prop test, and it may or may not be rejected. I can do the same for the oranges, the greens, and so on until I get one that's rejected. But the chi-square test is going to allow us to compare all of them at once and see, as a group, do they fit? That's goodness of fit. So rather than doing this as a 1 prop test, which you could, we're going to do a multiple comparison test. Now, in order to do this test, we need to come up with hypotheses and a measure by which to compare them. So the chi-square's null hypothesis, if you were to write it out in words, is the distribution fits the hypothesized distribution or the stated distribution, versus the alternative that it doesn't fit. You know, at least one of the colors is off in the case of the M&Ms. So it is not correct that the distribution is what they say it is the alternative hypothesis. Under the null, it is. It is what they say it is. The hypothesis can also be written out in terms of P, the proportion. Now, it's going to be a bit more cumbersome probably to do it this way, because you're going to have to identify each of the proportions individually under the null, define what that is. So P sub blue is the true proportion of M&Ms that are blue, and so on and so on. So you only have to define the 1P, but then you've got to do it for each of the colors there. The alternative, it's not that all of them are incorrect. It's at least one of the P sub I, which in this case is the color, is incorrect. And if one of them is off, the distribution breaks down. So we need to compare how many did we get versus how many did we expect to get. And typically, you're going to multiply the probability or the proportion of success to the sample size to get those expected counts. So in the case of the M&Ms here, assuming, let's see, we took 60 candies, that's our N in this problem, and 24% of them are supposed to be blue. So the expected number, I guess we could say E here, for the blue is equal to N times P, 0.24. And that gives us 14.4. So I'll put that in my table here. And we need to do this for all of them. We have to do it for all the different colors to get our counts. Now it's going to be 60, 60, 60, and 60 times the proportion of success, which for the orange was 20%, for the green was 16, yellow was 14, whoops, let's see, 13 for these guys, and 13 for those guys. And so some of them are going to turn out to be integer values, which tends to resonate with what we think about number of M&Ms. But when it comes to expected, you can think of it kind of like the predicted in multiple or in linear regression. Just because we had a prediction of aircraft that were flying at any given time, and it happened to be a decimal, that was still our best prediction. We didn't need to round up in that case. Same is true for the chi-square. Just because I get 9.6 as my expected number of greens, that shouldn't change anything. You don't need to round. That'll really throw off the calculation. So don't round for these expected values. And so I've thrown them in my table there. So ultimately, we want to see how far off is what we observed from what we expected, and that's the chi-square. So the chi-square test statistic is going to, maybe look kind of like the other tests where you have a statistic minus the parameter. But in this case, the chi-square, and by the way, it is pronounced chi, not chi. But the chi-square means I got to take a look at each observed value, and I'm going to look at how different it was from the expected. Just how far off was it absolutely? How many number of M&Ms was I off? Now, some of them, in a finite set of M&Ms, if I'm short in one group, I'm going to be over in the other group, and you could maybe imagine that if I were to sum up the differences, I'd end up with 0. So of course, what we do in statistics is we're going to square that. We're going to take all the differences, and we're going to square them. Hence the chi-square distribution. Now, looking at differences individually is not necessarily fair if you don't consider the total number that you've sampled. Because if I'm off by 1 for my expected 20 orange M&Ms, and I'm off by 1 for my expected 7 blue M&Ms, that one difference matters a lot more in the blue than it does for the orange. So not only do we look at the difference squared, but we want to look at it relative to what did we expect. So the chi-square is going to be each observed minus the expected squared over the expected. And then we're going to sum that. So it's the sum of each of those measurements. So in our example here, and let's just make sure we've got it here, and you can just write it as O minus E squared over E. That's probably going to be easier for you. Looking at each of these individual, and we'll do it by hand first. And if you want to pause here and try it yourself before you check out what I'm doing, now's the time. But it's the first observed minus the first expected squared over the expected. So that's my first term in this sum of which is going to be 6 different of these calculations. So plus, and then the next one, this is for the orange, 8 I observed minus the 12 I expected squared over 12. Plus, and I'll come down here for the greens. Now this one we had more greens than we expected. More yellows, we said that at the beginning, way more yellows than we expected. Over 8.4 plus 10 minus 7.8 squared over 7.8 plus 6 minus 7.8 squared over 7.8. And if you're probably already thinking, oh my gosh, there's got to be a better way to do this. Well, of course there is, and we'll talk about that later, how to do this using your lists. Maybe you could imagine, if I've got L1 here and L2 here, you could probably knock out this calculation and subsequent sum pretty fast. So if you want to take a minute to try any of those things, go ahead and pause. But by the end of it, we should end with a chi-square that's equal to 10.180. That's our test statistic for the chi-square. Now, remember that if all of these observed values were equal to all of the expected values, what would we get for the chi-square statistic? Well, if all the observed were equal to all the expecteds, that numerator would be 0. So the chi-square of 0 represents a perfect fit. So not statistically significant if you have a chi-square of 0. It is very hard to prove that it's different when it's exactly the same. But the more different the observeds are from the expecteds, the larger the chi-square is going to be. So larger values are stronger evidence against the null. And the chi-square is always going to be a positive number because we're squaring the differences. The chi-square statistic is one-sided. What does it look like? Well, like I said, it's one-sided where 0 represents a perfect fit. So I'll sneak that in there. And then the larger the chi-square is, the more significant evidence you have against the null. Something out here, for example. But it'll also depend on the degrees of freedom, right? The more categories there are, the more resistant it's going to be. So degrees of freedom of 4, for example, this orange curve, if I get a chi-square of maybe 8 or so, I'm looking pretty significant, by the time I get out there. But that's not true for degrees of freedom 8. A test statistic in that same position all of a sudden has a lot more area under the curve and is not probably significant for higher degrees of freedom. So the threshold for significance increases as the degrees of freedom increases. And the degrees of freedom, which is slightly different than when we think about the t-distribution, the chi-squared degrees of freedom calculation is the number of categories minus 1. So k minus 1, or maybe c minus 1 that we'll talk about later, but definitely not n minus 1. Because if you remember at the beginning of the problem, n was 60. So this does not have 59 degrees of freedom. This had 6 categories, or colors of M&M. So in this particular problem, k minus 1, 6 minus 1, we're talking about 5 degrees of freedom. Now you'll probably need to look this up. On my MIDI, I've got the stat tables posted on the home page there. And this will be the first time we've looked at the chi-square distribution. But given we've got 5 degrees of freedom, you're going to want to turn to that page, go to the row that has 5 degrees of freedom, and look for our test statistic. And remember, our test statistic was 10.18. So if you've done that, if you're looking at the table degrees of freedom 4, 5, 6, and then across the top are tail probabilities, and it's only right tail, that's all we have. So by the time you get to a tail of 15, I'll just copy it from the table real quick, otherwise I can't show you. And I'll look at 6, 5, and 4 degrees of freedom, and I go here to 0.1, and we've got 7.78, 9.24, 10.64, and I'm not by any means suggesting that you copy this down. You should be looking at your table, but you should be finding this area of the table for 5 degrees of freedom. We're looking right there. And our test statistic, chi-square equals 10.18, I understand it's over there, falls right there. Falls in between 9.24 and 11.07. Therefore, the corresponding p-value is going to be between 0.05 and 0.1. Right? Looking at the p-values up at the top there. Right? Once it falls there, we say, okay, it's in there. That's about the speed of the lesson for today. You don't need to really be accurate with any drawings of the chi-square distribution. They're all skewed right. If the degrees of freedom is insanely large, it'll maybe look more mound-shaped. But generally speaking, if you're sketching something, make sure it starts at 0. Make sure it's right skewed. That's as good as it needs to be. And then you won't really have a frame of reference until you've looked it up. But yeah, 10.18 is going to have between 5 and 10% in its tail area. So at this point, that's going to be the end of this set of notes. Remember that your task for Thursday, there's the Chapter 10 quiz that I'd like you to download, open in Notability, complete, and then to submit to Shobi. So I'll put that here. Submit to Shobi. Uh, and I just need you to do your best with that. You'll have all the resources that you normally should have available, your calculator, and try your best. Of course, I want you to get the correct responses, and submit it back to me, please. But that's just an assignment really at this point, but it is what we'll call the Chapter 10 quiz that we missed day 3 of last week. That's all to prop and to sample information. So that has everything to do with what we talked about last week, but it is something I'd like you to complete for Thursday. Relating to the chi-square, 11.1, homework out of the book, 1, 3, 5, 7, 9, and 10. Let's see, I want to make sure I didn't add another one. Good, no, that's it. I'll throw those in there. And be working on these things. Hopefully it's making some sense. And I'm gonna make myself available back on Zoom. So let's see, on Zoom, the last 15 minutes of our class period. So if you've run into any problems, I'll be on, and this is optional. You don't need to do this, but if you want to log back in and have a question asked and answered, with a smaller group of people, we can do that. Otherwise, that's your task, and I'll see you again on Thursday at the same time. That would be, I have on my calendar here, after lunch, which we call 11:35. Log back in on Thursday.